Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 39th lecture. In this lecture, we will be discussing placement. In the earlier lectures, we have seen that physical design is broken into multiple tasks which are shown in this figure, and in last two lectures, we had looked into chip planning. And after chip planning, the next task is placement. So, in this lecture, we will be discussing placement, and specifically we will be discussing these topics: global placement, legalization and detailed placement, scan cell reordering, and spare cell placement. So, let us first look into what does a placement do. So, the placement basically decides the location of standard cells. In the last lecture, we had looked into chip planning, and there also we had looked into the placement of larger entities. So, it is important to distinguish that what does the placement do. So, placement is basically deciding the locations of standard cells and not of larger entities. So, the larger entities such as the macros or the blocks that we have created by partitioning or the IO cells, those are actually placed during the chip planning stage. And in this stage, we are actually placing or deciding the locations of the standard cells. And where do we place these standard cells? So, the region for the standard cells were also decided during chip planning, right. Now, for each individual standard cell, we are deciding the locations in the region that was already allocated during chip planning. Now, what is the goal of placement? So, the goal of placement is to ensure the routability of a design, right. So, it is important to understand that the most difficult task in the physical design is routing the various entities in our design, and standard cells are the most numerous entities. They are in millions, and their connections are also very complicated. So, it will be in millions or billions connections or nets that we need to make connections, right. So, in physical design, and making those connections using the wires or interconnect on using various layers of interconnects, that is a really challenging task. And what does placement do? Placement tries to find good locations of the standard cell such that routing becomes possible, right. If the standard cell locations are not good, then there may not be any feasible solution, and then it becomes challenging to route our design and close our design, right. So, the primary goal of placement is to make or decide the placement of the standard cells such that routing is possible or routing is easy for the subsequent task, that is the routing that will be performed later in the physical design flow, right. Now, how do we assess the routing of a design, right. So, the placement, when it decides the location of the standard cells, it cannot do the routing. Why it cannot do the routing? Because routing itself is a very complicated task, right. For example, if we have one standard cell and another standard cell, there can be multiple ways in which this connection can be made, right. For example, one path is shown here, and there can be multiple other options which are available. And once the wire is laid out for, say, between two entities, then the routing of the next wire becomes difficult. For example, now if it can suppose these two were the cells, this cell and this cell, and we want to connect it, right. Now, we cannot connect it through the path because it can lead to shorting, right. So, routing of one net affects the routing of other nets also, right, and therefore, decide or assessing the routability of a design is a challenging problem. So, as an alternative, what does placement do is that it tries to minimize the total wire length of the design, Total wire length means that suppose there are n nets in our design, then for the sum of the wire length for each of the net is the total wire length of our design, right. So, in placement what does placement do? It tries to minimize the total wire length of our design. And intuitively what it means is that if we decide we minimize the wire length of our of the nets, then what it means is that if two cells are say connected through some pin, right, then to minimize it we will keep them these two cells close together, right. And if we keep them together, then in some sense routing becomes easier, right. And that is why the total wire length of the design is tried to be or that is the metric that on which the placement works is primarily the total wire length of our design, right. And there are other metrics also that are considered in placement, for example, timing, right, and congestion, right. Now, placement is a complicated task and therefore, it is done in various stages, right. So, there are three primary stages or tasks or subtasks in placement, and those are global placement, right, and legalization and detailed placement and post placement optimization. So, in global placement what is done is that the cells are spread over the core area, right. So, suppose this is our chip, right, and this is the allocated area for the standard cell. Then in global placement the cells are distributed or are placed on the core area such that they are well spread out, right, and also the wire length between them is tried to be minimized. So, the total wire length of the design is also tried to be minimized, right. Now, why do we want to spread out the cell, right? So, over the cell core area. So, the reason is that if we spread out the cell, then what is the routing resources that can be utilized better, right. So, understand that when we have cells, over them we have say 10 or 12 or 15 layers of interconnects, right. Now, these layers of interconnects are available throughout our chip layout, right. Wherever those are not already utilized, for example, for power lines or other signals, wherever they are not utilized, that is available for the routing. So, routing resource is fairly well distributed over the layout, right. And if we place cells well distributed over the layout, then routing resources becomes easily utilizable, and that is the motivation of the global placement to spread the cells evenly or well over the core area. Okay. And then during global placement, the dimensions of the individual cells are not considered, and therefore, there can be overlap between cells, and therefore, in the next step we carry out legalization and detailed placement. So, in legalization, overlap between the cells are removed by moving them further apart, and cells are moved to legal positions. For example, there can be some locations where the cell cannot be there. We remove those cells and put it the legal locations. So, what are legal locations? We will see in the later slides. And then after we have done the legalization and placed the cells over the layout, then we do some optimizations, for example, buffering, resizing, etc., to improve the QR of the design. Then in placement, so the primary objective, as I said, was to minimize the total wire length of our design, right. And therefore, for a given each net in the design, the placement tool needs to compute its wire length or estimate its wire length. Note that it is estimating, because the placement is not doing actual routing to compute to know that what the wire length is, but using some estimates it has to get that whether it is a good location or not, right. So, when the placement tool is doing finding the locations of the cell, so during the execution of placement algorithm, it needs to determine whether a given location is good or not whether it will lead to a small wire length or a large wire length, right. And therefore, wire length estimation is done many times for the nets in the during placement, right. So, ideally the estimated wire length should match the post routing wire length, but this is a difficult task because we are not doing the routing during placement, right. So, therefore, there are many heuristics which are used to assess or estimate the wire length of the nets during placement, right. And one of the most popular is half perimeter wire length estimation, right. So, in this method what is done is that it is an easy way to compute, and the half perimeter wire length is basically the half of the perimeter of the bounding rectangle that encloses all the pins of a net, right. For suppose we are trying to find a wire length for a given net, right. So, for each net will have 2 or more than 2 pins, right. Now, we first find a bounding box which contains, or the smallest size bounding box which contains all the pins in the of that net, right. And then what is the half perimeter of that bounding box meaning bounding rectangle. So, what is the half perimeter of that bounding rectangle? That is considered as the half perimeter wire length estimates of a given net, right. So, this is the most popular method of estimating wire length during placement. Why? Because it is very easy to compute, right. Just knowing the coordinates of the pins of a given net, we can easily compute the half perimeter wire length. It is very easy to compute and it is fairly accurate also, right. It for some type of nets it is accurate. For example, for say 2 pin and 3 pin nets, it gives very good it is accurate. For other big types of nets also, it also gives a fairly good estimate of the wire length, right. Now, let us take an example and understand that how the half perimeter, or it is also called as semi perimeter wire length of a net is estimated, right. Suppose that there is a cell, it is an inverter, and it is driving say 3 different inverters through a net, right. So, this is the net N, right. Now, during placement we are trying to find the wire length after we have placed the entity. So, we know the placement of this, and we want to now estimate that what is the wire length of this net N, right. So, we know the location of pin P1, P2, that is input pin of these inverters, P3 and P4, right. So, let these locations of P1, P2, P3, P4 be as shown in this figure. So, let this be P1, this is P2, this is P3 and this is P4. Now, we are asked the question, what is the half perimeter wire length estimate for this net N, right. So, first what we need to do is that we need to have a bounding box or rectangle which encloses all these pins, right. So, this will be the bounding box, right. So, we have created the bounding box by looking at the minimum and the maximum coordinates of these points, right. So, this is the bounding box we have got. Now, for this bounding box we compute the half perimeter. So, half perimeter means that if we count from here to here, right, either this path or this path, it will give the same length, right. So, we count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, the semi perimeter or half perimeter wire length estimate for this net N is 11, right. So, this is how the wire length estimate can be made for a given net, right. Now, this is a very simple method, or half perimeter wire length method is the most simple and widely used also. There are more sophisticated method of finding a good wire or more accurate wire length estimates. So, Now, how do we do the placement, right? So, what is the technique of doing global placement, right? So, the placement problem has been studied since long, maybe since 1970s, right? And it is known that it is a difficult problem, it is an NP complete problem, right? And therefore, a lot of heuristics have been developed over the years, last 50 years or so, for the placement problems, right? So, various heuristics have been proposed, and these heuristics work in good in some designs and may not work very well in other kinds of design. So, typically these days the most widely used heuristic of placement for placement is what is known as analytical placement algorithm, right. So, in analytical placement algorithm, or the way of, or the method of placing cells analytically, what we do is that we consider each cell as a point object, right. So, we can do, for example, if this is a standard cell, we consider, for example, the left hand corner, right, bottom corner, as its coordinate, or maybe the center of it, right. Center of this cell can be considered as the coordinate of the cell, right, and we ignore its length and height and so on. We consider the cells as point objects and assume that it is at some coordinate, say xi, yi, right. So, if this is the ith cell, then its coordinate is say xi comma yi, right. And then what we do is that we evaluate the cost functions such as the total wire length and the constraints mathematically, right. For example, we can consider the wire length as a function of the Euclidean distance. Suppose there were two cells, one cell was at say xi, yi, and another cell was at say xj, yj, right. So, what is the Euclidean distance between them? It is xi minus xj whole square plus yi minus yj whole square and a root over that, that is the Euclidean distance, and if we take the square of Euclidean distance, this root over will go away, right. So, in analytical placement algorithm, we consider wire length as a function of xi minus xj whole square plus yi minus yj whole square, right. And then based on that, we compute the total wire length or find the mathematical equation or math formula for the total wire length of our design, right. And then use efficient solvers to obtain the minimum cost for the mathematical formulations, right. Now, this is for these two cells which were connected. Similarly, there will be other cells which are connected, and then we take the sum of all these wire length and give it to a mathematical solver, right. So, formulate this in terms of say matrix equation, and then give it to the matrix equation to a solver, and which will give us a final result that these are the xi and yi coordinates for the cells, right. So, this is the what analytical placement algorithm will do, right. Now, if we directly give say minimize x, we give a function the total wire length phi, right, which is a function of say xi minus xj whole square plus yi minus yj whole square, and similarly other terms will be there. Then what will be the minima for this? What will be the minima? The trivial minima is of course when we say xi xj is equal, sorry, xi yi is equal to 0 comma 0, xj comma yj is equal to 0 comma 0. If we place all the cells at say one point in our design, we will get the wire length as 0, right, and that is the minima, right, mathematical minima, right. And this is of course not the solution why we want, right. We don't want this kind of solution. Why? Because if we place all the cells at one point, then the routing may not be routing will not be possible. The routing resources are not utilized over the layout, and so on. So, in the mathematical formulation, we need to modify it somehow. And what modification are required? The first is that there should be suitable constraints for the fixed entities. And what are these fixed entities, right? So, remember from last lecture that we have decided the locations of the macros and the IO cells, right. And if we have decided the location of those entities becomes fixed entities for the placement, right. And therefore, the location of the fixed entities which are connected, for example, there is a IO cell which is at this point, right. We decided its location during chip planning, right. Now, if the cell is connected to this IO cell, then it needs to be brought closer to it, right. It is not, it cannot be arbitrarily put anywhere, right. Similarly, suppose it is connected to another cell and this cell was connected to say another output IO cell, right, and this will pull the cell in the other direction, right. So, the constraints of the fixed entities will modify the solution, right, and that must also be given to the mathematical solver, right, or that should also be taken into consideration in the mathematical formulation. And also we want that these cells be distributed fairly evenly over the layout, and therefore, we add some cost terms, right, which are related to cell density, right. So, we can add some term in this mathematical formulation such that if the cell density is high, then that solution becomes penalized, right. So, these modifications are done by the analytical placement tool while formulating the mathematical model for the placement problem, and then giving it to to a solver to obtain the result. Now, the cells allow during global placement, the cells are allowed to overlap. We are considering cells as point objects. We are not considering them as say say their width and the height, we are not, or the length, we are not considering in this formulation, and therefore, there can be overlaps between the cells, right, and therefore, legalization becomes necessary after doing global placement, right. So, therefore, after global placement we do legalization. Now, what is an illegal location? A placement of a cell is illegal under a few conditions. What are those conditions? The first is that if there are overlaps, right. For example, if we take this is one standard cell and this is another standard cell, and there is an overlapping between these two, and therefore, this is an illegal placement for these two cells, right. And say, sometimes what can happen is that cells occupy illegal sites, for example, between the placement rows. For example, if we consider this one, this is not on the rows that we have assigned during or rows that we have allocated during the chip planning. So, this cell is out of that row, and therefore, this is an illegal location. And therefore, in legalization what is done is that it removes all overlaps and snaps cells to legal sites, right. And during this, it is tried that the minimum impact on wire length is there, timing is there, and congestion is there, right. So, the legalization process basically tries to make incremental changes or minute changes to the placement such that the problem of overlap and cells being in the illegal location, that is solved, right. It does not try to improve the or change the placement solution significantly during finding its or during legalizing, right. For example, in this case, if these two cells were overlapping and there was an empty space alongside, it will simply move this cell on the right, and it is this cell becomes legalized, right. Similarly, this cell was out of the row, it just simply pulls it into the row, and the solution becomes legalized, right. So, legalization do not attempt a large change in the placement, only snaps the cells or moves the cell by a small amount, so that the cells becomes legalized. And after legalization, then a detailed placement is done in which whose purpose is to basically improve the QR by incremental changes to the cell location. So, during detailed placement, some changes are made to the placement such that the QR of the design improves, and so it can improve the wire length and routability by making some changes. And what are these changes? It can swap the location of say two adjacent cells or neighboring cells, right, or it can redistribute the free sites over the layout, so that routing resources become available to the other area or other region on also, right, and therefore routability can improve. Or it can move cells to unused location. If the cell density is found to be large in some area, then it will try to move away from that location and put it in some unused location, right. Again, these changes are made in an incremental manner, right. So, the solution that was given by global placement, those are only perturbed incrementally during these stages, right. If we make larger changes, then it can perturb the design too much and can lead to design closure problems, right. We can just it can make the placement solution worse than what it started with, right, and therefore detailed placement does not try to make big changes in our in the placement solution. Now, we have discussed that the placement tries to improve the total or minimize the total wire length of our design, right. But for high performance designs and for industrial design, the timing driven placement are also used often, right. So, in what timing driven placement is done is that the placement tool internally has got an timer, or the timer basically the tool that does static timing analysis, right. So, what the placement tool has, it has got an internal timer, and it performs the timing of a design incrementally, right, meaning that if it changes the locations by small amount, then it can assess the impact of that change on the timing, right, and based on that incremental and internal timing analysis, the tool can identify or can evaluate that what is the slack of various paths, and there can be some paths which are violating, right. So, therefore, during placement, the paths which are violating, where there are negative slack, then those paths can be targeted by, or those paths can the timing of those paths can be improved by changing the placement solution, right. So, the timing driven placement basically targets either the worst negative slack, right. The worst negative slack means that given a design, what is the worst, what is the slack or the worst negative slack of our design, right. There will be many paths which may have a negative slack. Out of that, the one which is having most negative, that is the worst negative slack, and that is basically the path which must be targeted the first, right. And then there are placement timing driven placement tools which also target total negative slack. So, there may be thousands of paths which have negative slack, right. In that case, just solving the problem of top negative slack or the worst negative slack may not be fixing our design properly, right. In that case, we try to improve or improve the total negative slack of our design. Total negative slack means that we take the sum of the negative slack of all the points, all the endpoints which are violating the timing, right. And how does the timing driven placement work? So, the timing driven placement basically controls the proximity of the cells that are on the critical path. So, if the timing driven placement finds that this is the path which is timing critical, then the cells of those paths are placed close together, right. If the cells are placed close together, then the wire length between the cells can reduce, and therefore, the timing or the interconnect delay can be reduced for those for that particular path, right. So, depending on the placement algorithm, different approaches can be used to obtain timing driven placement, right. For example, during say analytical placement, what can be done is that we put additional weights to the nets to indicate timing criticality. For example, suppose there were two cells x, this has location x I y I, right, and this has got x j y j, right. So, the wire length between this can be estimated as the Euclidean distance between them, that is x I minus y I, sorry, x I minus x j whole square plus y I minus y j whole square, right. Now, in addition to this, if we find that these two cells were on the critical path, we can say multiply by a factor of this. In the cost function, we take it as 10 times of what this cost is, right, rather than multiplying by 1 or taking a function of simply the Euclidean distance square, we take it multiply 10 times of that, right. So, if we add additional weight to the nets to indicate timing criticality. So, if we give more weights to nets that are timing critical, then the additional weight will bias the solution of the placement solution such that these two cells are placed together, right. So, these two the placement engine will automatically place these cells together, because the weight of the nets corresponding to these two cells will be much higher compared to other nets in the design, and therefore, the placement solution will when the solver will try to find the placement solution, a solution in which these two cells are close together, that will be favored, and the timing of this particular path will be improved. Now, in earlier lectures when we were discussing test DFT, in that we discussed that one of the most widely used methodology for testing is scan based method. So, in a scan based method, just to recap, what we do is that we create scan chains, right. We replace flip flops with scan cells, and we create chains of or shift registers consisting of scan cells in our designs, right. And at when we did DFT, at that time we did not have the location information, right. So, we do not have the information of location of the flip flops or scan cells in the design, and therefore, the order of the scan chain, meaning that how in the scan chain which flip flop come first, then which, and so on, the order of the cells or the flip flops in the scan chain, that was pretty arbitrary without knowing the placement of the design. But after we know the placement of our design, then we can do some optimization. What we can do is that we can form scan chain or the ordering such that scan cells that are nearby, they form consecutive flip flops in the scan chain, right. So, let us take an example and understand what can be done. Suppose we built a scan chain initially. Initially, we did not know initially we did not have the information of the placement of the scan cells or flip flops, right. So, we made scan chain like this, right. So, from scan in it is going to say FF1, then it goes to FF2, then it goes to FF3, then FF4, then FF5 and FF6, right. Now, what is problem with this scan cell ordering? The problem is that it will consume more routing resource than it is necessary. For example, there will be a net which will be going from say FF1 Q pin and into the scan input pin of FF2, which is a scan cell, right. So, all these FF1, FF2, FF3, those are scan cells and they were replaced during DFT, right. So, if we consider the routing resource utility, this scan cell ordering is not a good one. So, what we can do? So, after we know the placement, after we have done the placement, we know the location of each scan cell, and therefore, we can reorder this scan chain such that routing resources are utilized more efficiently, right. So, this we can reorder something like this, right. So, scan in, from here it goes to FF1, then it goes to FF3, rather than FF2 it goes to FF3, and then FF5, then FF2, FF4 and FF6 and finally to scan out, right. So, it can easily be seen that the length of the wires in this case will be much greater, right, than in this case, right, and in that sense the routing resources will be utilized more efficiently in this solution, right. So, we will do this scan cell ordering after we have done the placement, right. Note that the of course, the test pattern for this case and this case will be different, but then test pattern can be derived later on after scan cell order. Now, in the VLSI design flow, we have seen that we do the implementation and we also do the verification. We are very careful that the design functionality remains intact, but sometimes what it happens is that a bug is found at later stages meaning that after we have done the tape route, after we have say created the mask, right. So, after we have created the mask and we have done the fabrication, and at the post silicon validation stage, right, we are getting some bug, right. Now, if we are in that situation, what can we do, right. So, remember that we for fabrication we need say 20 to 40 layers of mask, and these masks are very costly. Now, if we find a problem after we have already made the mask, then we have to do a respinning meaning that we need to make changes in our design and then do the fabrication again using new mask and so on. Now, the cost of this respin can be reduced if we say that we out of say 40 layers, we say bottom 10 layers which are say related to the devices, which those are not impacted, we need not change that, right. If we are able to do that, then the cost of respin can be much lesser than what it would be if we need to make changes in all the layers of our design, right. So, the spare cells are basically used in our design to help us avoid the entire respin of all the layers of the mask, right. So, what we do is that during designing we put on the layout some spare cells, those are extra cells in the anticipation of later use. So, those are not connected, right, those are not doing any functional function or the functionality of spare cells at that point of time when we are doing a tape out, that is not important. But later on when we need to probably do a respin, then we can use these spare cells and to fix the problem in our design, right. Now, what did we save if we use the spare cells? Now, spare cells are already there in the layout, right, meaning that those cells and the bottom layers which are of the design, right, bottom layers of the design where the cells are which are used for fabrication of transistors and the cells, those need not be changed, right, because the spare cells are already there. Only what we need to do is that probably make some changes in the interconnections of these cells or rewiring of these cells, and those rewiring of the cells can be done by just making changes in the top layer, topmost layers of or few layers of the interconnects, and therefore, the cost of respin can be reduced if we are able to find spare cells in our design which are not used, but but later on when a bug is found we can use them and those cells can deliver the functionality. Okay. So, after fabrication, if it is required that some cells need to be connected, then spare cells can be used because they are already there in the layout, and the features of the spare cells are already there on the device layers or the mask of the corresponding to the device layer, and those masks need not be changed. So, only the top metal layers might need to be changed, and therefore, the cost of respin can be saved. Now, we said that okay, the spare cells we will add some spare cells in our design. Now, the question is where to place those spare cells, right. So, ideally those spare cells should be placed where we think that those might be used, right. But when we do not know the problem itself in the first place, it is very difficult to anticipate where those spare cells will actually be used, right. So, we can think of that if some module is doing a lot of complicated functionality, then probably there may be some problem in that module, or it is more likely that some problem can be found near that in that module, and therefore, we can place spare cells where we anticipate that it will be required, right. If we cannot anticipate where the spare cells can be required, then we place them randomly over the unused placement area, and then probably when some cell will be required for making interconnection, then we can find some spare cells in its vicinity, because we have put many spare cells over the layout distributed randomly, right. But one important thing that needs to be considered here is that these spare cells, when in the layout, those are unconnected, right. If they are not used in our first layout, they are unconnected, and we need to do tape out with those unconnected spare cells. But what can happen is that sometimes the design tools can consider these spare cells as cells which are of no use, and they can optimize them out, right, to save the area of the cells and so on. And therefore, it is important to instruct the physical design tools and other tools where that these are the spare cells on the layout, do not remove them out, right. Those are not used for now, but they might be used later on, and therefore, they must not be optimized out, right. So, we must need we should be careful that our design tool is not optimizing this spare cells, right. Now, if you want to look further into the topics that we discussed in this lecture, you can refer to this book. Now, to summarize what we have done in this lecture, that we have discussed placement, right. So, we have looked into global placement, what is one of the techniques of doing global placement. Remember that global placement can be done in many ways. I have just taken one example, that is analytical placement method of placing standard cells, right. And then we looked into what are wire length estimates, then we looked into the detail placement and legalization and detail placement, and we looked into some optimization related to say scan cell, and also the placement of spare cells, right. So, after placement there could be some other optimization task that can be done, for example, buffering and the resizing of cells to improve the timing and so on, right. In the next lecture, we will be looking into clock tree synthesis. Thank you very much.